All right, now it's being recorded. Can you start your video?
No. Martin, are you able to do the video?
I'm not. I also get that message. You cannot start your video because the host has stopped it. And so, yeah, there's a little red slash through the start video button.
All right.
Which is, not a bad thing. I can stay still and not video. Do you want to do video, Dave? Are you gonna?
Well, I kind of wanted to. I mean, it's just going to show up as a little thumbnail, but it's better than
Okay.
not, in my view.
It's a great pleasure this afternoon to introduce the AIB interface that Intel is promoting as part of the open source community, along with Blue Cheetah. I think it's exciting technology, enables an entirely new world or ecosystem of design and thoughts about that. And so with that, I'd like to introduce Dave Kellett and have him introduce the team today. So Dave, and I'm recording this too, by the way.
Great, thanks, Rob. Hello, everyone. This is Dave Kellett, and I'd like to kick off the CHIPS Alliance AIB Deep Dive. So we have our required legal notice here. People who are familiar with our AIB journey will recall that AIB was invented to solve a die disaggregation challenge we had with the Stratix 10 FPGA. On the previous ARIA 10 generation, we had a monolithic device with high bandwidth die connections from the core to the transceiver columns as shown with the yellow arrows. When we selected Intel's 14 nanometer process, we wanted to reuse our transceiver design built on TSMC. The immediate question was, how could we connect the FPGA core built on Intel's high performance digital process to our TSMC process SerDes designs? Now, Intel had earlier invented EMIB, which gave us 7 to 8x the bandwidth density of standard packaging. So we built the AIB PHY using EMIB to bridge between our FPGA core and our transceiver chiplets. This chiplet-based design gives us great flexibility now to add new capabilities, such as RF ADC DACs like Jariots, without changing the core FPGA silicon. We used this chiplet capability in 2018 to add 56 gigabits per second transceivers to Stratix 10, the first 56 gig transceiver in the FPGA industry. This chiplet capability is very powerful, and it's attracted the interests of the US government. They've sponsored a series of projects from DARPA's CHIPS project, the Navy's SHIP project, and the RAMP project I'm showing here on the right. The US government sees chiplets and the AIB standard interface as part of their formula for keeping the US leadership in microelectronics. We would have called AIB Open AIB if we thought there was some question about being open. We're on our third year of open source with AIB, starting with RTL for the PHY in early 2019. As CHIPS Alliance, we've released the specifications for AIB 1.0 and 2.0, drafts of AIBO this year, and AIB 3D coming up that you hear about today. As CHIPS Alliance released the AIB PHY generator from Blue Cheetah, and a new model for AIB 2.0 is already out. This quarter, we will have an alpha version of protocol IP RTL released for running on AIB. The CHIPS Alliance is a great organization for promoting innovation, and I want to say thanks to Rob Maines, the CHIPS Alliance General Manager, for hosting this deep dive today. So I'm going to give you a look ahead here of the technical presentations that you're going to hear. Nij Doraraj is going to start off talking about AXI protocols on AIB. Then we'll have Krishna Settluri at Blue Cheetah talking about AIB and interface generators. Laguan Tang is going to talk about AIBO, which is a cost-optimized AIB for standard packaging technology. Farhana Sheikh will talk about AIB 3D. It's a proposed standard for 3D heterogeneous integration. And we'll wrap it up with Martin Wan, who's going to talk about the AIB chiplet ecosystem. So with that, I'm going to hand it off to Nij. And Nij, I'll page forward for you. Just let me know when to switch.
Okay, thank you, Dave. So today I'm going to talk about why we need like a standard protocol for die-to-die interface. With that, let me jump in. The first slide. I want to start with an introduction on how the current designs built, and then talk about the need for standard protocols and then I'll introduce the AXI4 or AIB, and then talk about what we're doing in this area. Next slide, Dave. Thank you. So how are our modern designs built? So if you look at current design trend and in the methodology, designs are more often IP based, and they're connected over standard protocol interfaces. And these interfaces could cover across MCPs, die, or chips. So what I'm showing here, this diagram below here, shows an example of an FPGA-based system. I have an MCP where or a multi-chip package. Within the package, I have ASIC talking to an Intel 10 nanometer Agilex FPGA over a die-to-die connection, which is again talking to another chip or a tile, in this case, Ethernet tile, which is kind of interfacing to the external world. And this So Dave, can you hear me? Somebody muted me.
There we go.
Can you go back, Dave? I'm not done with my. Yeah, this MCP can go on a board, which is again interfacing with another ASIC, and that's how the systems are built. And if you look at this, the blocks here, they are again connecting over a standard protocol interface. Next slide, Dave. So there's an increasing need for connecting over standard protocol. The picture on the right shows 2 chiplets over connected over AIB PHY over a die-to-die channel, and then an application is built on top of this chiplet. Customers are looking for a solution beyond the AIB PHY. They want to build application on these chiplets, and when you're building standard application, you want protocols to be enabled on these on top of AIB PHY. So what we have done here is we have built this in-between layer to enable application to talk over standard protocols and build like an IP-based system on these applications to enable like an end-to-end connectivity. And we wanted to do this over a standard industry standard interface, and we chose AXI4 for that. Next slide. So now I'll jump into talking about how the die-to-die connectivity is usually done. There are 2 broad protocols to connect between die-to-die. I'm showing here a streaming protocol. There are 2 examples that I have on the right side. I'm showing like an ADC or a DAC converter connecting to an SoC. Again, this is like you have like a sensor converter sending in data over to SoC. This is streamed into SoC, and there's another example of an Ethernet optical chip over a transceiver. Again, this is connecting to SoC over a stream interface. That it can be its own, in this case, like an Ethernet frame going into the SoC. If you look at these interfaces, right, it's a parallel data width. Based on the application, the size can be different, and usually streaming supports, kind of varying size. And you can have like an optional valid indicator from the source, or an optional ready indicator back from the destination to provide a flow control. Again, the main goal is to keep the utilization very high on these lines here, and you want this to be a low latency. This is exactly what AXI4 Stream offers, and that's one of the reasons why we picked AXI4 for these type to build the die-to-die connectivity. Next slide. Here's another another category of die-to-die connectivity. This is address read-write, where an example would be like a memory controller talking to or an SoC talking to a memory controller for reading and writing words into this DRAM array. So the main goal is for efficiently providing read-write access into the memory controller, and this is exactly what the AXI4 enables. A slight variation of that is like when SoC want to read and write into the control status register, it does something very similar to AXI4, but it's trying to economize the, because my performance doesn't have to be the same as memory controller, I can economize this connectivity and do like a low performance interface to read and write into the control status register. And this is exactly what the AXI4 Lite does. So what I've covered here is two major kind of protocol categories which AXI4 can enable. Next slide. So with that, what we really want to do with when I say providing end-to-end protocol, what we really want to do is to provide this type of interconnect here. So I have a chiplet A, which is an ASIC, and talking to SoC here over this AXI to AIB adapter, and through AIB PHY, connecting over AIB PHY. And within that SoC, I have my standard block where I'm building my application using standard IP block over, and then connecting to another chiplet C, in this case Ethernet. Again, I need my AXI to AIB adapter talking to or AIB talking to Ethernet. So you can see by providing this AXI layer, we have enabled like an end-to-end AXI connectivity, and this is this will ease the chip development because I'm able to bring in like standard AXI components on the SoC and talking to my chiplet over a standard protocol. Okay, next slide. So now I'll go a little deeper and talk about this AXI4 or AIB that we are building here. So I'm showing this diagram on the top shows an AXI4 leader and an AXI4 follower here. These are the two chiplets that I talked about on the initial picture. So essentially, what we are trying to do is between these two chiplets, we are enabling AXI4, and what we need to do in between to do that. So on a standard monolithic chip, you will be able to connect between the leader and follower, and you'll have the ready within the same cycle be asserted when there's a request. So this happens kind of naturally in the monolithic chip, but when you're doing this across die to die, you need to take care of a few additional things. One is because we are going to do a forwarded clock-based clocking, so we need to take care of the clock phase difference between the leader and the follower. And there's also additional delay that happens between the blocks that we are connecting to. So we need to kind of also handle that. So hence there's a need to build this AXI4 adapter to kind of deal with some of the die-to-die characteristics. So essentially what the AXI4 adapter builds is like a credit scheme to insert data on the leader side based on the credit availability, and also the follower will empty the data on the follower AXI adapter side and return the credit back to the leader. So essentially, you're building a credit scheme to kind of handle the some of the die-to-die characteristics here. And this allows, once you do this, then you're kind of abstracting out the underlying effects here, and you still provide an end-to-end AXI connectivity. So, and that's the reason why we are building this AXI4 adapter here. Next slide. So here in the next couple of slides, I'll provide some details on how this is actually done. right? Here's an AXI4 streaming example. I'm showing how the data is sent across from the adapter, from the leader to follower. Here in the first picture here, I have the leader to follower, where I have like a valid bit, and the data is just sent across. This is one of the example how you can actually send data from the leader to follower. In the second case, second picture here shows like a return, like a flow control back from the follower to leader. In this case, like a credit that comes back from the follower to leader, maybe like an Ethernet frame. It says, I need to kind of flow control this. And the third example is basically where you don't need to have like a ready or valid. You can just keep streaming the data, and you want the SOC to kind of react to it or handle this without any ready and valid. So this is all possible. But we have configurable ways to do this. So we'll allow non-byte quantities. The T data could be any size based on the application. Next slide. And here's an example for AXI4. AXI4, unlike like streaming, it needs 5 channels to be sent across the AIB wires. The transaction, basically, you will, for example, if you're doing like a write, you will be sending the write address followed by the write data, and there'll be a write response coming back. So you need to kind of send not just one wire or one set of data. You'll be having, based on a read or write, you'll have more than one channel that you need to send across. Next slide. Here's an example of how this is sent across, right? So it's all the 5 channels have to go through the AXI4 adapter to AIB PHY, and then cross the wires and go to the follower. On the follower side, again, you recover the AXI4 adapter, recovers all the 5 channels and presents like the AXI4 interface to the follower side. And the example here shows how a write data is actually sent across to the leader. You see like a write address where I have like a frame format, like or a packet format, where I have the AXI fields that are sent across, and write data, which is also packetized here and sent across. So it's an example of how a 64-bit data bus or AIB is sent across to the other side. Next slide. Here, so what I've covered so far is like a protocol that enables like an end-to-end connectivity. And what we're doing here is we're building the whole the connectivity IP that you need to connect between the leader and the follower. So that would be the AXI4. And I didn't talk about channel alignment. It's included in my slides here. Essentially, you need a way to align the data on the other side. That's another IP that we are providing. All this are done in a very, very configurable way, because based on the application, you would have different size and address needs. So there's an IP generator that provides this capability, essentially a configuration that you can input into the IP generator, and it'll give you like a leader side IP and a follower side IP, and you'll be able to plug it into your system and build your end-to-end protocol-based connectivity. So all this will be released as an open source in GitHub by end of this year. And there will also be like a support for this IP for 3 years after the release. You can build IP with this, and if there's any additional capabilities or fixes that we need, we'll be able to support that for 3 additional years. And that is my last slide here.
Great, thanks, Nij. Appreciate it. And folks, if we have time at the end, we'll take some questions. I'd like to get through the agenda first, please. And so with this, I'd like to introduce Krishna Settluri.
Thanks, Dave, and thank you everybody for your attendance. My name is Krishna. I'm the president and co-founder of Blue Cheetah. Today I'll be talking about generators, chiplet interfaces, and AIB. Next slide. All right, so to begin with, I think it's worthwhile to give a quick overview on who we are and what we do at Blue Cheetah. At Blue Cheetah, we specialize in the development of what we call as generators. Generators are effectively pieces of code that our designers write that capture the way that they go about designing circuits. Traditionally, things like layouts, choosing architecture, verification, modeling, or optimization. Instead of doing all of that traditionally and quote by hand, what we can do is we capture all of that designer knowledge in the form of executable generator code written in Python. Now, the benefit of doing this is not only does it enable kind of rapid configurability and actually going at the speed of software, but we're actually, as we'll show you in this presentation, we're able to do it in a way that enables process portability and going across different technology nodes and producing multiple variants and whatnot. Right? Next slide. Now, the core generator technology itself has been around for quite some time. Actually, we've been working on it for well over a decade now. The seedlings of the technology emerged from the founding team's work that we did at UC Berkeley. So it started back in 2010 with a tool called BAG, or Berkeley Analog Generator. And so since then, there have been improvements to make the framework, the API, and even the generators themselves more and more robust. Now, one thing that you'll hear me say maybe multiple times throughout this presentation is that one of the core differentiators to how we're going about developing circuits and generators is that we believe in putting the designer in the driver's seat or in the hot seat while they go about developing circuits, right? So we're not trying to replace the designers or automate analog. Instead, the analogy that I always use is it's like, taking designers out of an old car and putting them in a Ferrari, but they still need to know where to go and how to drive, right? And that's precisely what our API provides. Now, the API itself within the BAG framework is low level, right? So it enables designers to create design procedures. And as I said, it enables kind of rapid configurability and process portability as well to develop layouts at push button speed. It's worth spending maybe a few cycles on the figure or the diagram on the right-hand side of that slide, where at a high level, the framework itself is kind of divided into three levels, right? You have the circuit generator level at the very top, you have the BAG framework or the API level in the middle, and then you have the kind of the PDK primitives or the PDK specific information at the very bottom, right? So as mentioned, designers and competent designers are the ones that develop these circuit generators, and these circuit generators can take in performance specs as inputs, right? And depending on what the designer believes needs to happen with those appropriate performance specs, the appropriate design can be created, right? The circuit generator itself calls API and functions from the BAG framework, right? And the BAG framework has a whole slew of different functions and whatnot, but the key thing here is that the framework itself relies on existing state-of-the-art design tools. So we're not, recreating simulators or DRC or whatnot, but instead there are strategic hooks within the BAG framework itself that enable us to call simulators or DRC engines or whatever else within the circuit generators, again, by code. And last but not least, at the very bottom is what we call as these PDK primitives. And PDK primitives, you can think of it as effectively the Blue Cheetah representation of different PDKs. So different foundries have different PDK primitives. And so the key here is that by simply replacing or changing a pointer from one PDK primitives library to another, one can simply re-execute the generator and produce these verified sign-off instances on that appropriate technology node at push button speed. Next slide. So once again, this is what we call as our generator-based design approach. And as mentioned before, I'll say it once again, we believe in putting the designer in the hot seat. And so we capture the designer knowledge within these executable generators, and the generators themselves are only as good as the designers that write them. Our approach is not, we're not an optimization engine, nor are we an auto place and router of circuits, nor are we a GDS porter, right? Whatever the designers used to doing traditionally, that is precisely what is captured in the form of software. Right? And again, the benefits here is that you can kind of reuse the design methodology, you can enable parameterization and process migration like I was alluding to before. Now, one of the big key updates that has happened within the framework over the past year, the past couple of years, I should say, is the fact that now there's a robust framework to actually enable the production of, not only the netlist in GDS, but even the left-lib behavioral models as well. And internally, we ourselves are even pushing towards developing RTL and constraints in a very efficient generator-based methodology as well. And it's worth noting that the generator framework itself enables industry standard design collateral. So I'll show you examples of where exactly this was used in subsequent slides. But the fact is the material that you see as the final outputs is integratable. So it can be put into the SOC level or the systems level and pushed through kind of the synthesis and place and route flow there, and verification flow as well. Next slide. And so over the past couple of years, Blue Cheetah has been very busy. So we have been leveraging the generator technology in the core framework and API for a multitude of different projects, specifically on the die-to-die side and the memory interface side. And so one of our first big wins as a company at Blue Cheetah was actually this, the AIB 1.0 implementation. I'll talk about a little bit more on those details in the next slide, but where we showed generators for 22FFL and actually have silicon proven results there as well. In addition, we've had multiple continued projects with Intel. This slide is showing kind of the 1.2 project, which is a 24-channel variant, which leveraged the generator and the core collateral developed for the 1.0 project. On the other side, we also have worked tremendously on memory interfaces as well, right? So specifically on LPDDR4X, PHY, as well as a custom in-package DRAM variant of the PHY as well. Once again, I'll get into a little bit of the details here in the next couple of slides. Notice that the projects here were done on an advanced FinFET node, and it's also worth re-highlighting that the AIB generator and the AMS circuit generators themselves were released to open source sometime last year. Next slide. And so first we begin with a little bit more information on AIB. So as mentioned, Blue Cheetah developed full generators for all of the custom circuits, things like drivers, phase interpolators, delay lines, etc., leveraging the generator technology that we've been pioneering here. What's very exciting is that not only are those generators leveraged for open source, but they actually help produce instances on Intel 22FFL. And so we actually had silicon proven results on Intel 22FFL technology last year, where we demonstrated communication at 2 gigabit per second with the Stratix 10 FPGA. And so here we actually had the PHYs talking through the EMIB interposer to the Stratix 10 and vice versa. And there's actually further information on that in the press release as well. Next slide. And on the memory interface side, recently we had a very big milestone at Blue Cheetah where we actually have silicon proven results of our memory interfaces. And so in this particular case, generators were once again used to produce fully featured memory PHYs with industry standard interfaces. So this was an LPDDR4X PHY, as well as a custom in-package DRAM variant for one of our partners. And so in this particular case, generators were used to assemble the PHY circuit blocks themselves, as well as parameterized assembly at a slightly higher level. These were taped out on advanced FinFET nodes, and as mentioned, over the past couple of months, our team has been working very, very hard to get the silicon proven. And I'm excited to say that this actually does work silicon proven, right? So the memory interfaces were integrated into an SoC, and the full SoC, along with the interface, showed successful operation, right? It's also worth noting that for this particular project, our team did a tremendous amount more than just the memory interfaces. So we actually had generators for PLLs, DC-DC converters as well. And we were able to kind of tape this out with the resources I believe that we had, partially because of the benefits of the generator flow. Okay. Next slide. And so very quickly, just going back to the chiplet interface space, the chiplet interface space, as I'm sure we all know, it's a hotbed of activity. There is a tremendous amount of momentum that has accrued over the past couple of years, and it's only increasing moving forward. So there's a lot of adoption by not only the US government, but tier 1 semiconductor companies, as well as a whole slew of emerging AI and edge ML startups that not only believe in the chiplet ecosystem, but want to embrace chiplet interfaces themselves, right? But if we look at the space holistically, I believe the chiplet interface space, at least at this time, is still a bit of a wild, wild west. So there's a number of different standards, a number of different packaging technologies, and even the battle between closed standard versus open standard, that's all kind of being developed and pushing forward right now. But the key thing is that this is new territory and something that can potentially be very profitable for a lot of folks. Now, what we have seen is that there's a recurring necessity of users of chiplets and chiplet interfaces for rapid configurability and ease of use and ease of integration, right? And in fact, aside from that, there's also an importance for state-of-the-art power performance and area. So making sure things are low latency, area efficient and whatnot is also very important. Faster time to market, especially in the semiconductor space, is a universal must, right? That's always something that folks require. And obviously reduced risk as well to make sure that things are actually proven and working accordingly, right? And so we believe that not only are generators a great solution for that, but hopefully the next generations of AIB can really fit in and solve these problem statements as well, right? Next slide. So my final slide just leaves with a few logistics and potential next steps if folks have any questions. Blue Cheetah was founded in May 2018. We are led by globally recognized experts on the analog and mixed signal side, as well as the design methodology side. We are a global team now of 25 employees across the United States and all over the world. And we are we have full stack expertise at the company. So we have analog, digital software, PDK, firmware, all of that kind of under one roof, which I would argue is precisely the skill set that you need to tackle the problem statements that we have at hand. If you have any questions, please visit bluecheetah.com or shoot us an email at info@bcanalog.com. Thank you. Thank you, everybody. Thanks, Dave.
Great. Thanks very much, Krishna. Great to hear about the generators. So now I'd like to invite Laguan Tang to talk to us about AIBO. Laguan.
Hey, thanks, Dave, for inviting me to this forum, right? To give a presentations on AIBO, right? I somehow couldn't start my video, right? So sorry about that. So, but good morning and afternoon to everyone in the call, right? Depending on where you are. I'm Laguan from Intel PHY. I'm the architect for AIB, and we're focusing on defining the die-to-die solution for PHY. I'll be presenting AIBO, a cost-optimized solution for Judo ecosystem today. Right, next slide, please, Dave. Here are the outlines of today's discussion. I will start off with some die-to-die technologies backgrounds, then moving towards to talk about AIBO as a cost-optimized die-to-die interconnect. I will also go over the AIBO BUM plan and the considerations that associate with that, right? This is to show how we could achieve the bandwidth density through the innovative package routing. Next slide, please. This is an overview of the die disaggregation technology that is widely used within the industry. It is commonly referred to as a 2D, 2.5D, and 3D, right? Usually for the first category, which is what people usually call as a 2D, that is on the C4, and it has been used in multi-package solution. For example, between CPU and SoC, and usually through some link like PCIe or CXL. When people talk about the die disaggregation, usually what we think of is the microbumps, EMIB, silicon interposer, even 3D, right? But actually, all this can be used as a technologies for the disaggregation. And in terms of the wire density, right, it will increase from 2D to 2.5Ds and all the way to 3D. And same for the cost as well, right? I think we have a higher cost on 3D, and then less 2.5D will have less cost compared to 3D, and 2D will have a lowest cost. And for today's discussion, right, we'll focus on C4 and organic substrate as as an in-package die-to-die solution. Next slide, please, Dave. The right-hand side chart shows a different generation of AIB and its data rate as well as the bandwidth density. AIB 1.0 is the first generation here, right? It can be referred to as AIB 1.2 as well. And AIB 2.0 and AIB O is the next generation, right? But if you look at the AIB 2.0 and AIB O, right, the targeted data rate is the same. The difference is really on the channel or what we usually refer to as a packaging technologies. AIB O is on organic package, and then AIB 2.0 is on advanced packaging. So there are definitely some use cases that require high bandwidth, and for that we still need AIB 2.0 with the advanced packaging technologies. So certainly there are a lot of applications that doesn't need all the bandwidth density that AIB 2.0 provided. So AIB O does provide an interesting solution with certain bandwidth, price point, power, as well as the ease of manufacturing, right? A lot of the vendors out there has the capabilities to manufacture organic substrate, and this technology has been matured over the past 3 decades. And one key thing that right, thank you. One key thing that we could one key thing that I like to highlight is that we has been able to preserve the AIB interoperability between multiple generations, right? And this has been key for us to enable the chiplet reuse, right? Next slide, please, Dave. And then in lieu of all these benefits of and the use case of different type of channel, right? And also to maximize the reuse, I want to talk about a new concept, right? Basically, it's a single PHY design to scale for different bandwidth density. It can support both AIB 2.0 and AIB O. Natively, the PHY will be designed to match the numbers of microbumps for advanced packaging technologies. By changing the top metal layer, we could rebump to C4 and then connect the different numbers of IOs in the C4 versus microbump, right? In this case, we will be able to reuse the same PHY designs and then still meeting the different channel or the different packaging technologies, right? One key aspect that we need to keep is that we need to keep the per channel short line of 312, right? The AIB always has this short line. That this is the key for us to enable the chiplet reuse, right? And by doing by enabling the AIB on more cost optimized organic substrate technologies, we will be able to enable the disaggregation benefit without the high packaging cost. And one key that I would like to highlight is that this can be done with a 2-layer plus 1 microstrip line type of die-to-die routing, and it can be all enabled on the more standard 5-to-5 package, right? Next slide, please, Dave. And the diagram here shows the bump length of AIB-O, right? And the top diagram basically show the west coast and east coast of the bump length for AIB-O. And you can, the TX bump field is at the die edge, right? And in order for us to maximize the signal density and still maintain the shoreline, per channel shoreline, and as well as meeting the performance, the near end and far end bump fields are not made to be rotatable. We made some adjustments to the bound field in order for us to maximize the package routing. The next slide, I will show some diagram showing how we managed to do some different type of package routings to meet the signal densities, right? And so for a chiplet to pair with itself, right? Let's say for debug purpose or testing purpose, right? Some data swizzling at the PHY will be required. And the clocks we make it rotatable because the clocks are not it's not something that can be easily doing the swizzling, right? And the tables on the right that shows how you map the different data bits to a different pins at the East Coast and West Coast shoreline, right? For example, for data bit 0, right? In the East Coast, right, you maps to TXA, right? But on the receiving side on the West Coast, we'll need to map to RXB pin, right? So that you have a more straight line routings on the package, and then you have less jog, and then the more you do the joggings on the package, you impact the signal density on the packaging. If next slide, please. So this slide basically shows the 3-layer routing that we made to achieve the 8 signals per layers type of densities, right? And it includes the power and ground design in between. And we basically use micro strip lines and two strip line layers to do the routing. And all this can be done through, it's possible to be done through a standard 9/12 line spacing of the packaging rules, right? And we managed to do that with 3 layers. It is important to do it in 3 layers because that is the key for us to maintain the standard package form factor of 5 to 5 layers, 12 layers, right? Instead of increasing to more and more layers. Of course, when you increase to more package layer, let's say from 12 layers to 16 layer or even 20 layer, then you can pack more IOs and you can pack more signals per channel into the AIBO, right? That the spec does allow that. Next slide, please, Dave. So to recap, right? AIBO does provide a cost-optimized die-to-die interconnect for the chiplets, right? That is the main key driven factors for us to look at AIBO, and we will be able to utilize a single PHY to scale for a different bandwidth density, right? And we're trying to maximize the bandwidth density with a more commonly used package layer, right? It's not like we are trying to do it with a new package layer, which more package layers and or new technology on the organic package that will defeat the purpose of the introducing AIBO because we want it to be a more cost optimized, right? That's all for my discussion today, right? We'll take the question after after we went through all the agenda. Thanks, Dave.
Great, thanks very much, Laguan. Really great to hear about this. And by the way, everyone, you can find a AIBO draft specification under the github.com Chips Alliance repositories. So next up, we have Farhana Sheikh is going to talk to us about AIB 3D. So Farhana.
Hi, thank you, Dave. So yeah, I'm a senior engineer at Intel, and I work with Dave Kellett. And next slide, please. This is just a mandatory slide. Let's skip it. So let's quickly go over the motivation for 3D ICs and why we're actually looking at 3D integration and 3D standards for die-to-die interfaces. As Laguan said, there is now some interest in going vertical in terms of stacking dies, And there is an increasing use of 3D integration outside of just stacked memories. And we can see this in recently published material. Specifically, there's an example that I listed here is the Intel Lakefield processor that was published last year at ICCC. And that is a logic on logic type of platform. So what are 3D ICs? They're pretty much stacked silicon wafers or dies that are interconnected using through silicon vias or TSVs or copper to copper connections. And they're typically designed together by the same set of designers at a company. It's typically treated as a monolithic die. And so what people do is they design both dies together because they have to be able to interface nicely with each other and respect alignment and everything. And so people are typically using proprietary or simple interfaces and not really going outside to do third-party chiplet integration. However, this is going to change. We are seeing a number of requests for integrating third-party chiplets with even Intel IPs. And there has been some demand for a standard interface that allows you to do this in a very nice way without having to sit together and design the entire platform together. So that's what we're going to be looking at specifically today. Now, one of the nice things about AIB 1.0 and 2.0 is that they're open sourced die-to-die PHY interfaces, and they do enable high performance interconnect. So we want to leverage them as the basis for a 3D open source standard. Next slide, please. So some of the 2.5D die-to-die PHY standards that are out there, I've listed some of them here, not all of them. Obviously, it's not a comprehensive list. There's many, as was explained by Krishna and others today. But the top line is highlighted to show what the best possible energy efficiency we can get out of these standards. But for this eye chart, I really want to highlight the AIB 2.0 interface. And you can see that there's a very nice feature to AIB is that it is what I call a soft macro that can be turned into a hard macro. It's a generator-based analog mixed signal plus behavior RLTL design that can go across different process nodes. So depending on your choice of technology node, you can build an AIB 2.0 interface. And not only that, you can use it for die-to-die integration across different fabrics. We do see universities taking AIB and others taking AIB and wrapping it and using it for not just EMIB packaging, but over interposer and other types of die-to-die integration fabrics. And then the other nice thing is that it is open source. So we do desire a similar feature set as the 2D interface. And on top of that, AIB is familiar now to many people. And so basing it on AIB 2.0 is something that we do want to do. Next slide, please. So here, what I'm showing is first, what is out there in terms of 3D PHY interfaces. Now, the list is starting to grow. There's a lot of memory-based interfaces, as you already know, and then there's some new ones coming online. A lot of them are in the early stages or not open source. One example is G-Link 3D from GUC. It's very specific to TSMC's packaging technology, and it is not open sourced. You have to purchase the hard macro from them. And also, it's very early stage. Now, for us, what we want to do is we want to be able to support, as you see in the figure to your left on the top, we want to support an overdie type of integration of the PHY standard, and also on the shoreline like we're used to with our 2.5D standards. And we want this to be scalable across a wide range of microbump and TSV pitch, and this is just for future-proofing the standard. And you can see in the bottom picture here, it's a snapshot taken from a slide that was presented at Forum 5 in ICC 2021 by IMEC. And you can see that, there's a very wide range of pitches that are listed here, going all the way from a 3D SIP all the way to a 3D IC. Now, obviously, we probably don't need a standard for 3D IC when we're just stacking transistors, but for some of the other, types of 3D integration, it's quite possible that a standard would be required if you want to integrate some third-party IP with your own design. We want to be able to allow half duplex or full duplex operation. Half duplex primarily because we do see that, in case somebody wants to integrate a single port memory as on the base die, we want to be able to enable that type of integration. Also, we want to be able to enable point-to-point or point-to-multipoint links. This is because it could be that your top die would like to speak to multiple bottom dies all at once, and that's a point-to-multipoint link, and we want to be able to figure out a way to enable that nicely. We also, as I said before, want to be able to use this for both logic on logic and logic on memory. And then, of course, for clock correction purposes and clocking purposes, we do want to try to integrate a DLL in the picture, have a scalable number of channels, and then also for reliability, have lane repair and built-in test and pattern checking. And we do want to keep the feature of the standard to be very much like the regular AIB 2.5D standard, where it is generator-based or synthesizable. So it is what I call a soft macro. And then the other important thing here is that we want to be able to enable some non-intrusive power delivery. And this is something still very early stages. It's just at the thought level where Intel has announced some very interesting new 3D integration technologies where you can do power delivery from top side and through the side channels, as shown in this picture, where you don't necessarily have to drill holes through your base die to get to the top die. So let's move on to the next slide, please. So this is a high-level picture of what we envision the architecture to be. It is a 2D array of various signal bumps, and we've shown how we might intersperse power and ground, and this is just concept only for now. We obviously may, with some further analysis, we may change the way that we do the power and ground bump out. But as you can see, we can scale this array depending on bump pitch. So if we decide to target 25 micron bump pitch, which is quite viable today, we can have a 32 by 32 array in about 1 millimeter squared, which would support 512 bits TX or RX in half duplex mode and 256-bit full duplex mode. And allowing for 2 gigabits per second per bump. And this supports a max bandwidth of 1600 signals. So you can see that, if we do scale this to 10 micron bump pitch, we just basically can shrink the size of the patch to be 0.5 millimeter by 0.5 millimeter squared. And also because the bump pitch is scaled down, we can support a larger number of bits, 1024 bits in half duplex mode. We want to target 1 to 2 cycles of latency per direction, and of course include redundant bumps for repair. We would also integrate test and pattern generation because typically you don't have access to dies that are sandwiched in between dies, and you want to be able to figure out a way to test everything in a nice way, in an easy way. We do want to support logic on logic and logic memory, and we'll have self-protected IOs via ESD. And initially, we will be supporting only point-to-point links, but extending it in future to support point-to-multipoint. So when we figure out a way to do this very efficiently. So the other cool options that we do want to support here is that we want to be able to reorient the patch. So, for example, rotate it 90 degrees and still be integratable with your IP if needed. We want to support tiling. So if you wanted a larger patch, you could use multiple of these modular patches and put them together, and we can we'll sort of specify how you might do that in terms of both power and ground distribution and also clock distribution. And then we also want to be able to configure the number of channels. Next slide, please. This is something that we've sort of preliminarily worked out in terms of clocking schemes. And what we want to do here is we want to have the IP to be as light as possible in terms of circuitry. So very minimal circuitry that you want to integrate into your chip at the patch level. And so what we're doing here is we're supporting single data rate signaling, where the new data is actually transferred on one edge of the clock, and we're only forwarding one clock from the controller die, as shown here, where the top die is configured as a controller. So you can see that the TX clock is sent through to the base die and actually 180 degrees out of phase. And as it is received onto the base die, which is the peripheral die, a DLL is used for phase alignment so that the clock is edge aligned. And that edge aligned clock is then used to latch or flop in the data from the transmitter, which is the controller die, to the receiver, which is the peripheral die. So as you receive data out, you can send it off to either memory or compute. Compute is shown over here. And you can see that the picture on the left shows about a 1.5 cycle latency in that complete transfer. And then on the return path, as you are finished with your computation on your base die, you may want to send this data back to the top die, which is the controller die. And this is done using the same edge aligned and 180 degrees out of phase TX clock prime. So that data is flopped in and then sent to the top die through the buffers. And then it is actually received on the original TX clock, which is 180 degrees difference from TX clock prime. And that, again, that transfer, as you can see on the left, is also about 1.5 clock cycles. Next slide, please. And this is a picture showing what we're thinking about in terms of non-intrusive power delivery. On the top two pictures, you can see Intel's recently announced Foveros Omni and Foveros Direct. These technologies were also presented at Intel Architecture Day in 2020. And what these technologies allow you to do is to do power delivery in a way that it's non-intrusive to the base die. You don't have to make Swiss cheese out of your base dies. You can actually, using Foveros Omni, which is on the right-hand side at the bottom, you can actually deliver the power in between the base dies that are shown here, the memory and the ASICs, using the larger bumps as shown in the top picture. And then on the left-hand side at the bottom, you can see that Foveros Direct, which has been recently announced by Intel, allows you to deliver power from both sides of the die, so from the top and the bottom of the die. And so this is a very nice feature where it's completely non-intrusive to the entire packaged system. Next slide, please. So in summary, we are starting to draft, AIB 3D, and we are seeing increasing use of 3D integration outside of just stacked memories. The chiplet ecosystem, really, we want to increase it in the vertical direction. It does require these standard interfaces. And we want to leverage as much as we can from our previous work on AIB 1.0 and 2.0 and make sure that the AIB 3D standard is also open sourced and it is flexible across process. So it is what we call a soft macro. And we want to support a number of different options that are listed here. So yes, please keep an eye out for an early specification that's coming out soon. Your feedback is definitely important to us as well. Thank you.
Great. Thanks, Farhana. Really appreciate hearing about that. And next up is Martin Wan on the AIB Chiplet ecosystem.
Thank you, Dave. Hello, everyone. I'm Martin Wan, as Dave mentioned, senior member of technical staff with the Programmable Solutions Group here at Intel. I've been with the programmable logic industry a couple of decades now and had roles in customer applications, customer training, product planning, and most recently I'm here in the FPGA product group with responsibilities for our roadmap and overall portfolio. My talk is about how the AIB-based chiplet ecosystem has really helped Intel innovate its FPGAs in ways that would not have been possible or would have been much more difficult had we not taken advantage of it. And I'm going to be taking a much higher level view than the prior presentations, but I think it will really help to it'll help you to see the benefits we've gotten from this approach. So let's get started. Next slide, please. And thank you, lawyers. You're very familiar with our legal disclaimers now. So as Dave mentioned, Intel has been using AIB-based chiplets in our most recent FPGA product families, including Stratix 10, as well as Agilex. So this view shows at a high level that Intel is leveraging a chiplet library shown in the lower left that consists of many chiplets of different functions and also representing various process nodes. And by assembling various combinations of these chiplets into a single component using advanced packaging techniques, we have built all the members of our Stratix 10 series shown in the middle there, and also our latest FPGAs, the Agilex series, shown in the upper right. So pursuing this chiplet-based methodology has helped us to develop and deliver many industry-leading capabilities in our products. And in particular, in Agilex, we've got a 45% performance improvement compared to our prior generation, up to 40% lower power, PCI Express Gen 5 interfaces, Compute Express link interfaces, transceiver data rates up to 116 gigabits per second, and high performance integration of HBM2E memory. So I want to show you now in more detail how we use the chiplet library to use exactly the chiplets we need to target specific product areas. Next slide, please. So on the left, you see a box called Intel Chiplet Library, and you see a wide array of functions developed on a number of process nodes that really are providing the building blocks for complex, highly capable FPGAs. So these include various FPGA fabrics. So the logic, the DSP, the memory, the interconnect associated that you commonly associate with an FPGA there in the box on the left-hand side, as well as interconnect type chiplets like high-speed transceivers, PCI Express that you see there in the middle, as well as more specialized chiplets for specific capabilities like DSP and networking. Then on the right-hand side, you see a set of chiplets that are developed for specific applications like custom acceleration, custom I/O, custom compute functions, as well as analog functions like ADCs and DAC. So these chiplets on the right-hand side can be sourced from any IP vendor, developed on any process node using any foundry, and as long as they used AIB, Intel can integrate them into our FPGAs. So next slide, please. So as an example, let's take a look at how we use this method to actually build the Stratix 10 FPGAs. Our Stratix 10 GX devices consist of the chiplets highlighted in the green boxes, including a 14 nanometer FPGA fabric, PCI Express Gen 3, and 28 gigabit per second serial transceivers. And the result is a sort of a general purpose high performance FPGA family that supports PCI Express Gen 3 and transceiver data rates up to 28 gig. Next slide, please. Our Stratix 10 SX devices are intended for applications that need an integrated processor. So for this family, we use a 14 nanometer FPGA fabric with an integrated hard processor subsystem, or HPS, as you can see there in the box highlighted, the green highlighted box on the left, while keeping the interconnect tiles, the ones you see in the middle, the same. Next slide. In the case of our Stratix 10 TX devices, these are FPGAs intended for higher transceiver data rates and higher bandwidths. We continue to use a 14 nanometer core fabric, but now combine that chiplet with another providing 58 gigabit per second transceivers that you see in the middle there. Next slide. Our next Stratix 10 family is targeted at applications that are requiring the highest memory bandwidth. So we integrate a stack of HBM memory and continue to use the same core fabric and transceiver chiplets that we saw before. So you can see a sort of a repeating theme here. We're reducing our engineering risk and development effort by using technology that was proven out in prior Stratix 10 families, and then we enhance it with more application-specific functionality using whatever node, process node and foundry is best suited for those functions. Next slide. So now we can see we've added a PCI Express Gen 4 capability in our Stratix 10 DX families, as the one I'm talking about now. These were the first to offer, FPGAs first to offer that were certified by the PCI Express Special Interest Group for Gen 4. And you can see that we replaced the chiplet that provided Gen 3 capability with a new chiplet that provides Gen 4 capability and also added support for UPI. We also have an HBM option to address high memory bandwidth applications. And we kept using the higher speed transceivers to support the correspondingly higher IO bandwidth. So next slide, please. So in our most recent Stratix 10 family called Stratix 10 NX, we used a new fabric, an AI enhanced FPGA core fabric, along with the 58 gigabit transceiver chiplet and HBM memory that we introduced in the prior Stratix 10 families to offer Intel's first FPGA that is optimized specifically for AI applications. Next slide, please. So following Stratix 10, we've continued this chiplet-based methodology in the development of our Agilex FPGAs. And the Agilex FPGAs feature an FPGA fabric that is built on the 10 nanometer SuperFin process. So for example, I'm showing you our F-series, Agilex F-series devices, where we have paired that 10 nanometer SuperFin core fabric with chiplets that support PCI Express Gen 4 and transceivers supporting up to 58 gigabits per second data rates. Next slide. The other Agilex series shown here is the I series, and we use the same 10 nanometer SuperFin FPGA fabric chiplets as in the F series that I just showed you, but paired now with different combinations of interface chiplets, this time providing PCI Express Gen 5, Compute Express Link or CXL, and transceiver data rates up to 116 gigabits per second. So to provide even more differentiated capabilities that are targeted for different applications compared to our F series. So in this way, you can see that chiplet-based design has really enabled us to introduce new technology rapidly by building on a firm foundation of existing chiplets and then mixing and matching those chiplets using any combination of IP, process node, and foundry to achieve the specific functionality required. Next slide. So by now you can see that the chiplets that are available to us really broaden the functionality that we can offer in our FPGAs. So here's a list of the AIB-based chiplets, including many of the chiplets we've just discussed. And you can see a broad range of functionality. On the left-hand side, under the names chiplets, lots of different function names. Then these chiplets are built on several different process nodes. You can see, and the different foundries listed under the process column, and a source from many different developers. So over 20 chiplets so far, and more than half of them are in production or powered up, and more to come. So next slide, please. So I'd like to focus on two sets of chiplets now, and for the rest of my talk, the optical chiplets and also the data converter chiplets, providing functionality of analog to digital and digital to analog data conversion. So next slide. These optical chiplets were built by our partner, IR Labs, and they have helped to helped us to pathfind the ability to integrate optical interface capability into FPGAs. Optical interfaces between semiconductors have great potential to increase bandwidth, reduce latency, lower the power of device level interconnects, just as they've done at the board and system level. So we presented this technology at Hot Chips in 2019, and then we demonstrated it early last year at 2 terabits per second, and then announced a prototype to demonstrate 8 terabits per second interface rates at this year's OFC Optical Fiber Conference in June. So that prototype is shown on the right side of the slide, and you can see how we've integrated 5 of the IR Labs chiplets along with a 14 nanometer FPGA fabric die and also a transceiver chiplet into a single package. So we believe that these kinds of pathfinding activities are very valuable for exploring this next phase of device-to-device interconnects. And ultimately, they help Intel to be in the best position possible to offer a product in this space when the industry is ready for it. Next slide, please. So switching now to the analog chiplets that I talked about in the AIB chiplet portfolio, we did make a technology announcement earlier this year in January that we would be leveraging them in future FPGA products to deliver the industry-leading capabilities, namely the highest sample rates in our industry, up to 64 gigasamples per second. We call this direct RF FPGA technology. And the FPGAs equipped with this technology are targeted at applications like phased array radar, electronic warfare, test and measurement, et cetera, which strive to efficiently deploy digital beamforming. So with sample rates at this level, these FPGAs will be able to deliver 5 times higher bandwidth than the alternative offerings that are available today. And so the chiplet-based approach has also helped us to reduce power and latency, which is highly valuable to the target applications for these products. Next slide, please. So now going back to how we use our chiplet library to help develop products, now that Intel has high performance analog chiplets with delivering the data rate, data conversion capability for ADC and DAC functionality, we can integrate them not only with FPGAs, but also with other components from our custom logic portfolio, like eASIC structured ASICs and full custom ASICs, like I'm showing in the bottom middle of the slide here, to provide a range of options that offer different levels of flexibility and different levels of optimization for cost, power, and performance. So let me show you one of these examples or potentials on the next slide. So for example, we could choose to combine the analog chiplet that I'm showing you on the right-hand side, outlined in green, with a 14 nanometer fabric, FPGA fabric, and chiplets for PCI Express Gen 4 and 58 gigabits, providing a high degree of design flexibility combined with high performance ADC DAC functionality, as shown in this example. Next slide, please. We could also imagine a set of applications that need the analog I/O and ADC DAC functionality and custom acceleration, but don't require FPGA level of design flexibility. So to meet that need, we could combine the analog chiplet with a custom acceleration chiplet, also an eASIC die, and other interface chiplets as needed, like PCI Express Gen 5 or 28 gigabits transceivers to deliver a power optimized custom acceleration structured ASIC with ADC DAC integration. Again, these are potentials products that we can offer now that we have this analog capability available to us. Next slide, please. So to conclude, with the preceding examples, I think you can see that AIB-based chiplet design certainly has provided Intel with several development advantages, including options to integrate functions regardless of the process node, foundry, or developer. As well, we have access to a much wider range of functions that are developed by the chiplet ecosystem and can more rapidly innovate our product development as a result. So the innovation in the chiplet ecosystem has also helped us to pathfind new technology areas like optical integration and integration of high-performance ADCs and DACs. And with options like these, clearly our ability to deliver industry-leading capabilities to our customers is enhanced. And we've already announced plans to do so in the area of high-performance analog I/O integration. So that's my last point. Appreciate the time you spent listening to my presentation and to those of my colleagues. And I'll turn it back over to Dave.
Great, thanks very much, Martin. Okay, folks, we have a few questions that have come in, and so we'll take a chance to answer those that have been submitted so far. I'll take the first one here. This is from Ketan Mehta, who asks, are there limits on how many chiplets and along all edges that can be integrated? Really, it's on a single die. We have been able to put chiplets on all 4 sides of the die. So there's really no limit on how many chiplets and edges that you can use. Now, really, the limit is you start connecting multiple chiplets up in a pipeline or spanning them out in 2 dimensions. It's going to be your packaging technology. You know, how many different connections can they support? If you're using an interposer technology, that may have reticle limits with it as well. And other technologies like EMIB don't fundamentally have it. It just ultimately gets to the reliability and complexity of building something as big as you really want to do it. So thanks, Ketan. The next one is from Anonymous. And Laguan, I wonder if you're on, you might talk to this one here. Can you connect heterogeneous chiplets, different process nodes? Does that affect the bump map available for lower nodes?
So I can take that, right? I think, so today, most of the process node does enable different types of bump plan, right? So let's say you are talking about the AIBO, right? I think those are on C4 and is a very matured technology. But if you're moving towards and it should be already enabled for all the process nodes, right? The min pitch and all these things are standard. But if you're moving forwards to 2.5D or even 3D, right? For 2.5D, I think today I believe most of the foundry does already have that capabilities to enable a micro bump pitch, and we should be able to based on the pitch size that are available for that process technologies that scale the bump plan, right? And 3D will be more gearing towards the process node that is being enabled as a base die as for the 3D.
Great. Thanks, Laguan. Let's go on to the next one from Charlie Wishbard. By the way, folks, Charlie is the CEO of IR Labs, and he asks, do all the chiplets in the library support AIB or have plans to? Martin, can I
Sure.
ask you to take this one?
Yes, I can take that. And thanks, Charlie, for joining us. And appreciate shout out to IR for the fantastic work as our partner for the optical chiplets. So I showed you in that slide, certainly every chiplet that had a green outline around it, where I was showing you how we built the different products, those have AIB. There are some that are, we think make sense, that maybe in development or on various levels of research and early research and looking at whether or not it makes sense for a product in that space. So, they all represent, I think, real valid use cases, is what I would say. And, the list of AIB chiplets there that I showed also sort of indicates all the different areas that are actually in active development as well. So I hope that answers the question.
Great. Thanks, Martin. All right, next one up from Mohammed Islam asks, can you please comment on the various ways to mitigate noise induced from power TSVs to signal TSVs used in the Foveros Direct architecture? Farhana, you want to take a shot at this one?
Sure. So, so we haven't actually looked at fleshing out the Foveros Direct architecture yet, but some of the ways to mitigate noise is always to put in some buffer between the signals and the power TSVs, and to do some careful power routing. But again, you have to be mindful of how you want to align the power grid on the top die with the bottom die. So this is something that we'll have to really carefully think about and get back to you on that.
Great, thanks, Farhana. Next one is from our friend Tim Lee, who asked, for the chiplet ecosystem, does Intel have a plan to put real-time processor, e.g. ARM Cortex-R5, in the HPS besides the quad ARM Cortex-A53? So Martin, I'm going to ask you to take that one, please.
Yeah, sure thing, Dave. So we have, so thanks for calling out that our current HPS includes quad-core A53. So, we certainly have the capability to integrate real-time processors like the ARM Cortex-R5. We have not announced any plans to do so. So, should we discover or should we understand that there's a business case to do so and that our customers would benefit from it, we would, that is something we could consider for our future products, but we have not announced anything like that at this time. So thank you for that.
Great, thanks, Martin. And we've got another one from Tim Lee, who asks, any idea when the AIB 3D spec will be released? So Farhana, would you take that, please?
Sure. So we're releasing an early draft sometime in the fall, and please keep an eye out for it. And Dave will let everybody know in Chips Alliance when it's out.
Yeah, let me just add that we have an AIB working group as part of the Chips Alliance that it's free to join. And if you want to join in, we will discuss stuff like the concepts behind AIB 3D. We're already reviewed by the Chips Alliance AIB working group. As the specification law evolves, we can we'll have further discussions there, and contributions from any of the folks there are welcome. Okay, I think we have another one here. Okay, this question comes from Mitch Bailey. For stacked chiplets, how do you verify connectivity? LVS question mark. Do you use proprietary software or Calibre? Farhana,
sure, I can take this. So there is an IEEE standard out there for verification purposes. I believe it's IEEE maybe 838 or something like that, but I can get back to you on that one. But there is an IEEE standard that's been out there for few years now, and so that actually specifies how you could actually verify connectivity or verify die-to-die connectivity in a vertical stack. And I am looking at that in addition to possibly other ways of doing that.
Okay, thanks, Farhana.
Farhana, this is Rob Maines. I'm sorry to interject here, but this was kind of in line with a question I had actually. And so is there anything relative to electrical verification for the 3D stack that you're looking at?
Yeah, so
In
that's
terms
where
of
that.
timing, go ahead, sorry.
Yeah, go ahead. Yeah,
No,
so go ahead. I mean, go ahead. Sorry.
no, that's my fault. I was thinking like in terms of timing or noise or power, but I guess just even something, well, I would say simple. It's not simple, but just in terms of timing interfaces, how that's done.
Yeah, so there's all stuff that, you know, it's not a very easy thing to come up with all of this technology for 3D integration of third-party IP. So, you know, we're looking at all of these things and, you know, they're looking at all the different ways that people are potentially doing this today, maybe even looking at the way that, you know, stacked memories are doing this. You know, the IEEE standard is something that I found maybe 6 months ago that I was surprised that it actually existed. So that's something that we will think about and try to figure out what's the best way to do that in terms of verification. And then self-check and self-test, that's another idea that we did have as a requirement where we can integrate some of that already into the standard itself. So it allows you to, it gives you some feedback on how you're doing with connectivity and reliability.
Thank you.
Great, thanks, Farhana. And Mitch has a second question. The presentation today featured physical connections between chips. Have you considered through chip interface, which uses magnetic waves to transfer data between chips? And I'll take a shot at that. Yes, you know, we've heard of some research that's been done on wireless communication between chips and ideas on how to do high bandwidth wireless communication. So this is definitely an interesting topic that we will stay in touch with here, because you know, that could unlock a whole other ability to transfer without being limited by abutment or shoreline. Okay, any other questions? People are typing in. Looks like we might have.
I think you have one. I think you have one more. Yeah.
Okay. Mark Beal asks, I'm interested in the AXI over AIB. Has thought been put into natively switching or routing the new packetized format? And I'm going to ask Nij if he'd kindly respond to this one.
Yeah, let me, this is Nijar. Yes, so one of the key things that we are trying to do here is to keep the bandwidth efficiency really, really high across the AIB, given we have limited number of channels that we have to send this data across. One of the solution that you can do with the current support that we offer is to use this type as an in-band coming over the data line, and then you have the option of kind of routing that from on the SoC side, kind of like a router on the SoC, like a soft router. You could adopt that, and that works fairly well. And we have recently kind of tried some of those mapping to simulate that, and that'll be the preferred option. Obviously, given the AXI standard, if you want something native, that will need to, you need to kind of allocate some bandwidth for that. But we are recommending that you go on the in-band.
Great, thanks, Nij. Okay, folks, we are coming up at the end of our time here, and I would just like to say it's fantastic having this opportunity to talk to everyone here and hear from our presenters today. And with that, Rob, I'll hand it back to you, please.
Thanks, Dave. Hey, I want to second that and thank all of you for all of your work on this very interesting topic and providing a good detailed overview of the many different considerations that go into this technology. I think it's exciting. I think it is a fundamental game changer in changing the ecosystem for innovation in the industry, and really will help move us things forward. So thank you again. Thanks to the audience for listening to our talk today. I hope you enjoyed it all, and it will be available for a replay as well. So with that, I will end the meeting. So thanks, everybody.